One of the key players in modern neural networks is the attention mechanism. So the attention mechanism somehow can be understood as a way of how a token is affected by uh, other tokens, or how a piece of an output is affected by uh, other pieces or from the different pieces of the input. So for instance, this can be very well understood in the context of sentence translation. So let's say that we have this uh, sentence in German, and if we want to translate one by one the words, you can see that the translation in English sounds very weird. Can you me help this sentence to translate? Uh, Somehow the third word, can you help? Uh, the third word in English has to look at the fourth word in German. So these are which words are or which tokens should be paying attention to which tokens in the input is this mechanism of attention. And the same concept can be applied to images or to any other kind of data. So there will be two key components in this attention. One is that the words are embedded into vectors, so that each word, the input is encoded as a one hot encoding. So every word has a code, and then you put each word in the sentence. Each word in the sentence you put it as a vector of zeros and ones. All zeros except for 1 1, and then that input vector, binary vector, has to be embedded through typically a network. So you put here another network that you will learn that produces these vectors that we call x. So each one of the words will be x0, x1, x2, and so on. Okay, the other component of the attention mechanism is a kind of dictionary. So we are used to dictionaries, for instance, in Python, in which you have a key, and then given that key, it will return a value. So for instance, if your dictionary is about the full name of a state in the US. So if you give CA, the value will be California. If you give OK as key, then the return value will be Oklahoma. But you can have a dictionary of what is the unemployment rate in the different states, and then California will have its number, Oklahoma will have its own number, and so on. So what we will learn in attention is a dictionary, and we will combine the outputs of this dictionary depending on what is the word that we have at that moment. So let's do that step by step. I have taken most of these pictures from this blog entry, and actually it describes the process very well. So if you're interested in seeing the full explanation by him, you may go to that URL. So let's say that we have the different words, so x1, x2, xt. So typically when you work with these kind of systems, you limit the number of words in the sentence. So typical limit could be 1,000 words. So if your sentence is longer than 1,000 words, you cannot represent it. If it is smaller than 1,000 words, then you fill with some padding kind of seal. Okay, so for each one of these words that are coming from these embeddings, so for each one of these embeddings, we will construct three other vectors that are called the query, the key, and the value. So from this word, from this embedding, we will construct a query, and the query is constructed by simply multiplying by a matrix. So if your input vector is of size d, then this matrix is of size dk times d, so our keys and our queries will be of size dk. And then we will construct the value, that the value is this one multiplied by another matrix that now it has a different output size, dv. Okay, and we do the same for the input words, input word embeddings. Then this is what we did before. So from that word, let's say that this is our the word we are interested now. So we have the query, the key, and the value. And now the query is the query in this dictionary. So it will not be, so now the keys will be vectors. They are not labels as here. So the key is a vector, the value is another vector. So our query here will not be one of the vectors that we have stored. So actually there is no storage. It is just a kind of implicit dictionary. But our query will not be one of the keys, but it might be similar to some of the keys. So what we will do now is compute the similarity between our query and the keys. So query 2 with key 1, query 2 with key 2. The comparison is done through the dot product. And then these are these dot products. And these dot products are normalized somehow by the dimensionality of your key. So now we have the normalized attention scores. So this is called the attention score, and this the normalized attention score. Okay, good. Then now we have the attention scores for each one of these queries. So we have different values. So we have the value associated to the key 1. So x1 produces k1. So x1 will produce a key in the dictionary and a value in the dictionary. So we have all the similarities between the query 2 to all the keys 1, 2, and t. And then we have all the values. So all we have to do is a linear combination of the different values according to these attention normalized scores. So that will be our output, and this is the attention mechanism. So given a word, we will produce a value. This value is a combination of the values of all the other tokens in the word, in the sentence, but with different scores. These scores have been calculated by the normalization of the comparison of the query produced by the current word and the keys of all the other words. So we can represent that now. We have presented vector by vector, but we can put that into matrices, and then we have the input matrix that has number of tokens and the embedding size, and then we have the matrix that transforms that into queries, the matrix that transforms that into keys, and the matrix that transforms into values. And then we have the comparison between all the keys and all the values, and so all the queries and all the keys. So all the queries and all the keys, it is q k transpose, and it has n times n. This is the attention matrix. So this n times n has the same size as the number of tokens. And then we do the softmax, that will gives you the normalized attention matrix. And now we have to multiply, so construct the output that is a weighted average of these values according to these attentions, and this will be the outputs, and the outputs will be one output per input token, and the size of that output is dv. So actually attention is nothing more than local smoothing. So local smoothing is a problem, a statistical problem, in which you are given pairs of x, y pairs. So every point here is an XY pair. And here we are drawing in one dimension because it is easier to draw, but the predictor and the predicted values can be n-dimensional. So what we want to do is that for any point here that would be our query, we want to predict what is the value of this function given these samples of that function. So given that those samples, this point here, somehow what we will do is a local average of those points. So we will construct the kernel. So this kind of regression is called the Nadaraya-Watson kernel regression. So for the input query x, we compare x to all other xi's in our data set. This would be the dictionary keys, and then for each one of those keys we get what is the value. So what is the value associated to each one of these points, and depending on whether the query is close or far from the value from the query, then we will add more or less weight to that value. So if this point is if the query point is here, then we will give a lot of weight. The kernel will be high for these values around, for these y's around, and it will be low for these ones around. And then what we have is, for instance, if our kernel is Gaussian, then all these points will contribute a lot to the target point, that is this query that we have. And this will be the value that is a weighted average of the observed values around. Okay, so this is the comparison between the two problems. So in this local smoothing, we have a query. So we have here in the neural network, we also have a query vector. So we have some keys that are the locations on the x of the points that we have observed. So we have some keys, and now we also have some key vectors, k. We have some values that are the ones that we have observed. We have some value vectors, and then we have to compare the similarity between, or how close x is to all those keys. We do that through a kernel. So we do that through a similarity between the query and the keys, and then we have to normalize. So we have to normalize here, so that we sum overall the whole sum of comparisons of kernel similarities, and then we estimate f as the weighted average of the values. So that will be our attention output. So actually that is this set here. Okay, and here we will do it in two steps. So trying to modify the local regression problem into the using the same notation as the queries and keys and values from the attention mechanism. So now we are given keys and values. So we have a query vector. So we compute the similarity between the query and each one of the keys, and we normalize by this, and we compute the weighted average of all those values. If now we define this part as alpha, so these alphas are the attention scores, the normalized attention scores that we defined before. So we have a query, then for each one of the values in the dictionary, we have an attention score, and then we average according to all these attention scores. And we can represent that in matrix form. So the matrix form will be, for instance, we have this similarity matrix S, that is Q, K transpose, where we have here in Q, we have the matrix of all queries. Here we have the matrix of all key vectors, and here we have the matrix of all value vectors, and the query vectors, the key vectors or these vectors are row vectors. So each row in the matrix is one of the vectors we are interested in. So if we multiply this, the element ij of S is the similarity between the query I and the key j. Then we take that similarity matrix, normalize and apply the softmax. So this is this normalized attention mechanism that we had before, and then we simply multiply by V. So this is the weighted average of the V values according to this attention scores. So again, making the comparison between the neural networks, the self-attention, this kind of attention that is called self-attention, and the local regression that we had. So we had input data points. Now what we have are keys and values, and then we have also a query. So now we had to compute before how far my query was from the observed data points, and then here we do that by similarity, and then the output is a weighted average of that. And now the key thing is that in the standard local regression, the bandwidth was fixed. So how wide the Gaussian kernel was fixed. Now we can learn somehow the kernel through learning these three matrices. And there was a local averaging of the nearby points, but now the prediction is no local anymore, because we can we are calculating here, we saw it in this attention matrix. This attention matrix, all vectors are compared to all vectors. So that means that we can take any word in the sentence to predict my third word if I want to. Okay, so more about this comparison. So this the kernel regression was a weighted average of values. So the attention is learned, data dependent weighting, but now in the feature space. So not the values are also learned. And the softmax of the dot products acts as an adaptive kernel, and these matrices help us to learn representation space, where this kernel that is somehow fixed in the sense that there are no parameters becomes meaningful. And the stacking of multiple attention layers corresponds. So if I do one attention layer and then it is followed by another attention layer, so that means composing multiple learned kernel smoothers. So it is a kind of hierarchical regression. So we do that regression on the output of another regression, and we do the regression on the output of the next regression, and so on. Okay, so this is the self-attention mechanism, the basic of the self-attention mechanism. But now there are a lot of variations on that. There is one that is called flash attention, that it has to do with how all these calculations are performed in memory, and there are a lot of so typically the typical equation of attention is this one. So there is a lot of matrix multiplication that is occurring here. So how we organize that in memory so that we can play with static RAM or this. So the GPU RAM, the GPU, whatever kind of memory this is. So this memory is very small but very fast. This memory is slowest but larger, and then the CPU RAM that is very slow compared to these ones, but you can have a lot. So how to arrange flash attention is just how to arrange the calculations. Then we can have multi-head attention. So multi-head attention, what we have explained here is the single head attention. So you have a set of vectors here, and then you learn WQ, WK, WB, and you do the attention scores, and then you compute the output that is a mixture of these values according to these attention scores. That is for a single head, but now you can put many one after the other, and then instead of making one regression you would be doing three regressions, each one with their own kernels. So this is multi-head attention. And then you could have cross attention. So the cross attention, before we had a single sequence of tokens. In cross attention, we have two sequences of tokens. So one, for instance, this is very useful when you are doing translation between languages. So you have a sequence of tokens coming from one language, another sequence of tokens coming from the other language. They have to be embedded into the same space, so a space dimension, and then you do the construct your queries, and these queries from one language, they are accessing a dictionary in the other language, and then the dictionary in the other language will produce some values, and then the rest is just the same as in the standard self-attention. And here we have a nice representation of the cross attention. So for instance, in English we have the agreement on the European Economic Area was signed in August 92, and in French this European Economic Area is translated, the word order is reversed, this Zone Économique Européenne. So it means that we have this zone has to pay attention to area, that cannot pay attention to European, and here European has to pay attention to European and not to the sixth word. Okay, so what we have studied is global attention. So all tokens can influence any other token, and the problem is the computational cost. We may assume, especially for instance for images, this is particularly true, that a token, so a pixel, has an influence in the nearby pixels, but not in all the pixels in the whole image. So this keys comparison and the values coming from the keys can be local. So if you are in pixel I, you can take a neighborhood, perform the regression locally. We can also have masked attention. So sometimes in some contexts you want to prevent a token from looking into the future. This is particularly true, for instance, if your sequence is made of stock prices. You don't want your neural network to look into what happened into the future to predict what will happen now, because that in real life that is not available. So then what you can do is this matrix of attention scores, then you can mask so that all these elements are not accessible. So you set them to 0, or you ignore them during the next calculation so that they cannot influence. And you can also extend this idea to graphs. So in graphs we have seen you have a sequence, then you can have, for instance, in local attention, a token can be related to the neighborhood. So this is the local context where you will compute will make the comparisons. In graph attention, you can extend that idea further so that each one of the nodes can be compared to the keys of some of the nodes. So the query coming from node 0 can be compared to the query to the key of 0 and to the key of 4, but cannot be compared to the key of 2. So the graph defines who can be compared with whom. Then we also have other accelerations. So for instance, this is the standard attention that we have already explained, and this is the weighted average. So this is the weights, and this is the values, and the attention is this thing. So the problem with that is that this comparison is quadratic. So you have to look to make a lot of comparisons, n versus n. So the trick here is somehow to compute lower rank randomized matrices. So instead of computing Q, and full K, what you do is some low rank matrix Q prime and K prime, and somehow work with those matrices. And then this paper here describes how to do that. And that technique is called performance. So this is all for self-attention, and see you in the next video that is about transformers.